Good morning, children. Okay, so today we're going to start the waves part of the energy units. You got 4 sheets on the notes, just doing the first 2. Let me pull them over to the screen where I'm recording. So, what is a wave? Pictures, all this writing stuff, and that's it. The things about the behavior of the waves we're going to do later. So, just doing the first 2 pages today. Are you ready? If not, you can always hit the pause button until you get ready. But I'm ready, so here we go. There it is. Waves. It's all about energy moving from place to place. So here's the definition of a wave. Repeating disturbance or movement that transfers energy through space or matter. Pause, write it down, and then come back to me. Welcome back. Alright, so question for you. What do waves carry? On the notes it says carrying matter or energy question mark. They carry energy. They only carry energy. They do not carry matter. Waves do not carry matter with them. Now I know you're going to think they do, because some of you will anyways, because you've been to the beach before. Alright? And that's a little better. And when you went to the beach, you maybe went out to the water with all the fish poop and the sharks and whatever. And a wave, what you call a wave, grabbed you and maybe knocked you down or pushed you back to shore. What you're feeling and experiencing there are the breakers. When the wave bounces off the coast and goes back, and energy goes back out into the ocean, some of that energy from when the wave piled up, gravity pulls it down along its front edge. That's called the breaker, where the wave breaks. That water is flowing down the front of the wave, and so it has velocity towards you. It can actually pick you up and carry you. The wave will not take you anywhere there. If you go out past the breakers and you're floating out there in the ocean, you notice as the waves come by, you go up and then back down. And you don't end up going anywhere. Currents can take you somewhere, but not the waves. Okay, so waves only carry energy, not matter or people. Use your brain power to answer the following question. You got it? The answer is energy. But you knew that already, because you're smart cookies. Mechanical waves. So, there are 2 types of mechanical waves, and they both need a medium. Transverse and compressional. Another way to say compressional is longitudinal. Okay. You'll run into it at some point in your life. Someone will call it a longitudinal wave, but now you know they mean compressional wave. Both of those types of waves need matter. Without matter, they can't travel. They have to travel through matter. Alright, the matter through which it travels is called the medium, and you notice it says both need a medium. This is what a medium is, the matter through which a wave travels. Any matter can be a medium. Air is the medium for the compressional waves I'm making. Alright, the speakers on whatever you're using to listen to me are putting those compressional waves back out into the air as if I'm making them for you. Alright, water, waves go through water obviously. Waves can go through the earth, earthquake waves. Any matter can be a medium. Each type of mechanical wave has its own unique effect on the medium, and that's what we're going to look at eventually. We're going to now look at what those types of waves do to the medium. Transverse waves make the medium move back and forth at right angles to the direction of the wave. I want you to write that right here, above the picture of a transverse wave. Let me move this out of the way. Alright, so transverse waves make the medium move back and forth at right angles to the direction of the wave. What's a right angle? Make that a loser sign on your head. That's a right angle, if you're holding it right, I guess. It's 90 degrees. Okay, now the next slide is going to be an animation. Hope it shows up properly on your screens, showing you what a transverse wave does. Yeah, are you ready? Here we go. Okay, so you notice this darkened in part right here, so you can see what each individual particle of matter is doing. When the wave goes by, it goes up, then down, then right back where it started. The wave is going to the right though, so the wave is moving at right angles to the direction that the matter moves. It makes the matter move at right angles to the wave's direction. See? I hope so. Alright, next slide will be compressional waves and their definition, or rather what they do to the medium. These make the medium move back and forth in the same direction as the wave. That goes right here. We'll get back to the picture in a little bit. That goes right here, beside the word compressional. Boop, boop. Write it down. Pause if you need to, because I'm about to hit the button in 3, 2, 1. Boom. No, there it is. Boom. Alright. This animation shows you what compressional waves do to the matter. There, now I'm looking at it. Uh-oh. There we go. And you see the matter gets squeezed forward, pulled back to where it came from. So the matter is still not going anywhere. Alright? The wave is, but the matter gets moved and then put back where it came from. So the wave affects the matter, but doesn't end up moving the matter, if that makes sense to you. Alrighty then. Let's take this picture right here and make sure that everything that's on here and labeled is also labeled on your notes. This picture right here. When you printed it out, some of these words may not have shown up very well. They still look kind of on my monitor. So take a moment, stare at this picture. Okay, and if you need some more time, go for it. I'm going to hit the button now. You can always pause. Boom. These are the parts of a compressional wave, also called the longitudinal wave. On here is an area called the dilation, where the matter is stretched out between two waves. It's also known as a rarefaction. In fact, on the North Carolina final, they usually use the word rarefaction instead of dilation. So that's why I have that on here. Make sure it's labeled on your picture properly. Make sure you put the word rarefaction on your picture. The compressions here and here. So between two compressions is a rarefaction. Okay. On this one, the wavelength goes from right here, the middle of one wave, to right here, the middle of the next wave, or the next compression. So from compression to compression is the wavelength on a compressional wave. This is the best picture I could find on the internet for this thing. This is time 1, time 2, time 3, time 4, time 5, time 6. This is showing that the two compressional waves traveling along a spring over time. Pick one of these 6 and use it as the one you label. It doesn't matter. Alright, if you need some more time, pause, and I'm going to move forward. Where's the energy? So we're on the second page of the notes. Right up in here. In a compressional wave, energy is found in the compression. Remember, waves are carrying energy. So some part of that wave is where you find the energy the wave is carrying. In the compressional wave, the energy is in the compression, where the matter is squeezed together. In the transverse wave, the energy is found in the crest. Drinking water, staying hydrated. Alright, moving forward. Where's the particles in the medium rebound after the energy of the wave passes through them. So it's kind of like a basketball. When you throw it up and you miss, it rebounds. You can catch the rebound and throw it back up if you want to, or it rebounds against the ground. And whatever. So the rebound in a transverse wave is the trough, where the matter bounces back past where it came from before it finally gets back up to its resting position. In a compressional wave, it's in the rarefaction, the stretchy out part. Alrighty. So we've compared where the energy is in a transverse and a compressional wave. We've compared where the medium is rebounding. These are called equivalent parts of the waves. Alright. Another equivalent part can be the wavelength. For transverse waves, the wavelength is measured from the crest of one wave to the crest of the next wave. I mean, technically it could be any part on one wave to that exact same part on the next wave, but let's just make it easier from crest to crest on a transverse wave. On the compressional wave, I just told you, but we're going to repeat it. It's from the center of one compression to the center of the next compression, from compression to compression. Pause if you need to write that down. I'm going to move on. Amplitude. All right. Transverse wave, it was the height. That was labeled on there for you. Actually, let me rephrase that. It's not the height. It's from the rest position, which is that straight line going across where the matter would have been if there was no wave going through, up to the top of the crest. That's the amplitude. That's how much the wave makes the matter move. Okay, so it's from rest position to top of crest for transverse wave. For compressional wave, amplitude is a measurement of how tightly the matter is squeezed. You and I can't put a number on that. All right? It's just a concept I need you to understand. The tighter the compression on a compressional wave, the greater its amplitude. All right? Okay. What controls amplitude? Because that's an important thing. What controls amplitude is the amount of energy the wave is carrying. So more energy means more amplitude. Less energy means less amplitude. Okay, you've got that. If you need to go back. You can pause. The next concept is frequency and period. Definition of frequency is the number of wavelengths that pass by a single point in 1 second. Measure it in hertz. You can pause if you need more time, and we're going to move on. Oh, sorry. 1 hertz means 1 wave per second. Period is defined as the amount of time it takes for one whole wavelength to pass by a fixed point. Being a time, you measure it in seconds. Pause if you need to, and then come back. Okay. Can you figure out how frequency and period are related? You can go ahead and pause here if you need to. Fast. Okay, so hopefully you figured it out. If not, here it is. They are the inverse of each other. Inverse is a word that I learned in high school. I think y'all learned the word reciprocal. Yeah, the same thing. 1 over the frequency equals the period. 1 over the period number equals the frequency. So think about it. If 5 waves pass by in 1 second, each wave takes 1/5 of a second to go by. Does that make sense? Let's try another one. If 2 waves go by in 1 second, each wave took half a second to go by. 2 over 1 for the frequency, 2 hertz. 1 over 2 seconds for the period, half a second for the period. You getting it? There, now it won't vibrate the desk when it goes off. Okay, I hope you'll understand that concept. Next thing is the equation for today. Yay! Calculating wave speed. Oh, that's a bunch of symbols, isn't it? That's okay. So v subscript w means velocity of a wave equals the frequency times the wavelength. Upside down y, as y'all keep calling it back when we were in class, is the Greek letter lambda, lowercase. So v sub w is the velocity measured in meters per second. Funky f is the frequency in hertz. It's supposed to be an italicized lowercase f, but just lowercase f, that's fine. And lambda is the wavelength measured in meters. Yay! That's the end of the slideshow. You're going to have some worksheets that, bigger. You can have some worksheets that make you use that equation. So I want you to think about this. If velocity is frequency divided by wavelength, then frequency is going to be velocity times wavelength. And wavelength is going to be what? So wavelength would end up being velocity divided by frequency. Okay? Alrighty then. Y'all enjoy the worksheets? Yeah, right, enjoy, whatever. Try them. Answers will be provided. And I will see you next time.